In this video, we're going to talk about acid strength and dissociation equations. Let's review some things that we know about acids. Acids are covalent compounds. Their formula consists of nothing but nonmetals. But they're special covalent compounds. They're ones that form ions when they dissolve. They have formulas that begin with H. That's how we know that they're acids. The chemist who wrote the formula was typically kind enough to indicate the presence of an acid by beginning the formula with an H. And the ions that they form are H plus ions. They donate them, they get rid of them. And here's the new part. Acids can be both strong and weak, and we're going to talk about the distinction between those two. Strong acids completely break apart or ionize when they dissolve. Take a look at this bar chart. Let's say we've got a general acid, HA, and it's a strong acid. Let's say the full height of this orange bar is 1 mole. When that acid is dissolved completely, I have just about 1 full mole of H plus ions and 1 full mole of A minus ions. That is what's left, the conjugate base of the acid after H plus is donated. And if I were able to zoom in on the solution and see exactly what's found in the solution, I would have nothing but broken apart H plus and A minus. There'd be no intact acid left. So in a strong acid solution, many H plus ions are found in the final solution, and the concentration of the acid matches the H plus concentration in the final solution. So if it's a 1 molar concentration of the strong acid, you'd have a 1 molar concentration of H plus ion in the final solution. Contrast that with the behavior of weak acids. Weak acids remain mostly intact when they dissolve. Take a look at this bar chart. If the height of the orange bar represents 1 full mole, you'd have like 0.99 moles in the final solution of HA. And you'd have 0.01 moles of H plus and 0.01 moles of A minus. So you'd have lots and lots of intact acid molecules, HA, in the final solution, and just a few ions. So in the final solution, there are a few ions. And you're probably wondering, how can we describe mathematically the extent to which a weak acid ionizes? Well, you can guess that teachers love to draw connections between units. We're going to connect acids and bases to equilibrium. We're going to write an equilibrium expression. That's part of the fun here. Okay, some things to know. There are hundreds and hundreds and hundreds of weak acids out there. There are only 7 strong acids. Now, I used to have my students memorize this list, and to some extent that may still be helpful time saving for you. But I will tell you in any problem that we encounter in our class, whether it's strong or weak. Nevertheless, here are the 7 strong acids, just so you have a familiarity with them. Hydroiodic acid, hydrochloric acid, hydrobromic acid, sulfuric acid, nitric acid, chloric acid, and perchloric acid. Arranged in this way and just focusing on the negative ions, not the hydrogen ions. A student of mine in the past came up with this mnemonic: ickle, bro, so, no, clo, clo. Ickle, bro, so, no, clo, clo. It's just a way to remember the 7 strong acids. Okay. For a general acid, here's your equation. H plus, HA, the acid formula, and H2O react. HA becomes A minus, H2O becomes H3O. I want you to focus on that H3O for a second. That H3O is called hydronium ion. Now, if we simplify this equation and say, okay, that hydronium ion is really a proton, it's an H plus ion with an attached water molecule. What if we just are aware that water's around and we kind of subtract H2O from both sides of the equation? I see H2O here, And if we can imagine a hydronium ion is H2O attached to an H plus ion, we got rid of the excess H2O, we can greatly simplify this acid dissociation equation. HA yields H plus and A minus. We call this a simplified acid dissociation equation. And the reason it's useful is it shows how the acid breaks apart in solution. Let's try practicing writing acid dissociation equations. Here's chloric acid. Let's show the difference between the full acid dissociation equation and the simplified one. Chloric acid is HClO3. And if it's the full acid dissociation, I'd show it reacting with H2O. I'd show H3O on the product side and chlorate ion on the right side. Chlorate is your conjugate base. Hydronium is your conjugate acid. Now, if we subtract H2O from both sides, realizing that hydronium is an H2O attached to an H, we get this. HClO3 yields H plus and ClO3. It's much easier to write this simplified acid dissociation equation. I'm going to switch over to a Jamboard here and do a couple of practice ones with you. Let's say we're given HBr yields H plus and you fill in the blank. What does HBr become after getting rid of H? Well, we're going to be left with Br. Now let's think about the charge. HBr was a neutral charge and H plus ion was gotten rid of. So to balance the charges on the right side of the equation, the left side's neutral, the right side's got to be neutral too. So one chemical species that's +1 would cancel out one chemical species that's -1. How about this one? HC2H3O2, that's called acetic acid. If it yields a proton, what's left? I'm simply going to rewrite this big scary acid, but without the H, or the H in front. I'd be left with C2H3O2. What about the charge? It was neutral to begin with, and when it kicked off a proton, it got rid of 1 unit of charge, so its charge went down. It's now a -1 charge. Okay. Charge is important. Let's connect this to equilibrium. If our acid dissociation equation is the general acids dissociation equation, HA yields H plus and A minus, then if I were asked to write an equilibrium expression, I would write K equals, and then I would look to the product side of the equation. I'd put H plus in brackets, times it by A minus in brackets, and put all of that over the reactants. It would look like this: H plus times A minus all over HA. One little thing you'll notice after that K, you see a subscript A. You don't have to include that, but it stands for acid. And if you were to write a dissociation equation for a base, you would put Kb. If you write the ion product constant for water, you would write Kw. Little subscripts kind of indicate, hey, this is the situation that we're applying the equilibrium constant to. And in this case, it's the acid. Okay. Strong Ka values. If this is our acid dissociation equation, and this is our equilibrium expression, and we remember that in the final contents of a strong acid solution, it's nothing but the ions. Well, strong acids have high concentrations of broken apart H plus and A minus. They have low concentrations, probably 0 concentration of intact acid molecules. And their Ka values, as a result of that, would be wicked huge, very, very large. In fact, so large that they approach infinity. Why? Well, students, consider how we calculate K. If in the solution, there's nothing but H plus and A minus, let's say it's 1 molar concentration of H plus and 1 molar concentration of A minus, and and we divide all of that by the concentration of the intact acid, which is almost zero, maybe even zero, dividing by something close to zero, or let's put it this way, the smaller your denominator in a ratio, the higher the value of the ratio. That's why you're getting wicked huge Ka values. Contrast that with weak acids. Same equation, same equilibrium constant concentration. Take a look at this final contents of solution. It's mostly intact acid. Weak acids have low concentrations of broken apart H plus and A minus. They have high concentrations of intact acid molecules and thus small Ka values. Think about that from a ratio standpoint. If your HA concentration is large, that means your denominator in the ratio is large. If your H plus and A minus concentrations are small, that means your numerator is small. If you take a small numerator divided by a large denominator, you're going to get a small ratio. Oh, okay. Weak acids, if you compare them, they do have different Ka values, but all of them are quite small. Take a look at this table. Here's a chart of several different Ka values for weak acids. They range on the bigger side on the order of 10 to the minus second, but then they get much, much, much smaller. 10 to the minus third, 10 to the minus fourth. Some of the smallest ones, like phenol at the bottom here, 1.6 times 10 to the negative 10th. So Ka values for weak acids are very, very small. Ka values for strong acids are very, very large. Thank you for your good work today.